Hey, good morning. First of all, we have homework on Chapter 8 that's due Friday, so in 2 days. So first order of business is, are there any questions about homework number 8 that people wanted to ask? Well, if you have questions, you can always try to email me or stop by my office. That's due Friday, and then the next homework assignment won't be due the next Friday, because that will be the Friday after Thanksgiving, but the week after that. And that's on Chapter 10 that we're going to start today. Chapter 10 really has 2 pieces to it. It has a part about feedback, which we'll discuss probably next week. And it also has a part on nonlinear dynamics in general and chaos. And we're going to start on that today. Just as a reminder, the last class will be really, I think, the day that the homework's due, and then Friday, and then the following Monday, the first possible time, will be our final exam, Monday morning, 8 to 11. So keep that in your plans. Okay, so what we're going to do today is we're going to go over a couple of the problems in the homework, really the last 4. But mainly problem 40 and 41, or 41 and 42, excuse me, which are kind of long-winded. We're going to do those problems, except we're going to use a slightly different function for what's called the restitution curve than you'll use in the homework. So you'll be doing almost exactly what we do with just one slight modification. So hopefully that will give you a head start on the problem. Okay, so what is problem 41? Well, it talks about action potentials. And it basically says that if you have cardiac tissue that's at rest, and then you stimulate it, so a little dot here is going to represent a stimulus, you'll fire an action potential. And the action potential will go for a while, and then it'll come down, and it'll be over. And the duration is called APD, action potential duration. And then it'll be back to being flat again until you stimulate. Then you get another action potential. Well, this time after the action potential ends and before the next one begins is called the diastolic interval, DI. And the time between stimuli is called the coupling interval, or the coupling length, CL. So let me just write those down. APD is action potential duration. DI is called diastolic interval. Now, where did that weird name come from? Usually, the heart can be said to either be in diastole or systole. Systole is when it's contracted. Diastole is when it's relaxed. So, in terms of its action potential, systole is during the plateau of the action potential, and diastole is during the resting period afterwards. So, this would be a time when it's in diastole. And CL is usually known as the cycle length. And all of those are in milliseconds. So we're going to be analyzing them in milliseconds. Now, the thing is that if you have a very short diastolic interval, you're going to have the next action potential be affected. It'll still fire an action potential, but in general, the next action potential will be shorter, have a shorter action potential duration. So we're going to get some interesting dynamics related to the length of the diastolic interval and the length of the action potential. And you can see almost immediately that the action potential duration plus the diastolic interval is going to equal the coupling length. So those aren't independent parameters. And in fact, if you know what the action potential duration is, say of the ith stimulus, say there's a bunch of stimuli, the ith stimulus has a certain action potential duration, then you can just take the coupling length and subtract off that, you can figure out what the ith diastolic interval is. So we have this relationship di, the ith case, so the ith stimulus, is just going to equal the cycle length minus the action potential duration from the ith stimulus. So we know how to get diastolic interval once we have action potential duration. Now the hard part is getting action potential duration for the next action potential if you know the diastolic interval. And that has to do with what's called the restitution curve. And the restitution curve is what's different between your homework problem 41 and this example that we're doing in class. So the restitution curve is basically a relationship. It says the action potential duration for the I plus 1 stimulus is going to depend on the diastolic interval from the previous case. And it's going to depend in this kind of weird way. 300 times the diastolic interval for the I stimulus over 100 squared plus diastolic interval I squared square root. Okay, so that's a weirdo function. Let's see how it behaves. Well, in order to see how this behaves, let's plot it. Let's see if we can figure out what it's going to look like. This is going to be diastolic interval, and this is going to be action potential duration. And they're both in milliseconds, so this will be 0, 100, 200, 300, and then the same tick marks here, 0, 100, 200, 300, and both in milliseconds. Okay, so now we got a little work to do. We got to figure out what this function looks like. What happens if the diastolic interval gets really long? What's this function going to be equal to if the diastolic interval is very long? So who can help me with that? Take the diastolic interval, assume it's really big.
It should be 300.
It's going to be 300. This is going to be very big compared to 100. So if this is big, it's just di squared square root. So that's di downstairs, but there's a di upstairs. They cancel. So this is going to go asymptotically towards 300 at very large diastolic intervals. Now, what does this equal to if di is very small? If di is very small, well, you ignore this di compared to 100. So this is just 300 over 100, so it gives you 3 times the diastolic interval. So it's going to start down here at 0, because at small, when di is 0, action potential duration will be 0. And then it's got a slope of 3. So it starts heading up linearly like this. And now I'm going to put in some numbers that I calculated. So it gets up to around 50, it's up around 100, close to 150, at about 100, it's up for a little over 200. At 200, it's up around 260, that ballpark. So it goes like this as it asymptotically approaches it. So here's your restitution curve. It's heading up towards this dashed line. So all this says is if you tell me that the diastolic interval is very short, then the next action potential is going to be very short. And if you tell me the diastolic interval is very long, the next action potential is going to be about 300 milliseconds. Okay, so this is the setup for the problem. Now what we want to do is we want to start actually doing these calculations. And this is where hopefully some of you brought your calculator so that you can, so we can do these calculations together. But I'm going to have to erase some of this to make some more room. So, any questions on this before I start erasing it? Okay, here's your picture. There, you want me in the picture? Okay. Here we go. Hopefully have room to leave this up here. Okay, we have action potential duration. First of all, we're going to specify what the cycle length is. In this case, I'm going to use a fairly long cycle length of 400. The action potential can even get up to 300 is its longest amount. So this is going to be what would be a fairly long action potential. And we're going to make a chart here of action potential duration and diastolic interval for each stimulus. And you got to start somewhere. So we're going to assume that there was tissue was at rest for at least 100 milliseconds before the first stimulus. So that means the first diastolic interval is going to be 100. Now, what is the next action potential duration of the next stimulus? So this fires. What's the duration of this action potential? How would you calculate that? Well, you take 100 and you stick it in here. So anybody has their calculator out, get 100 divided by square root of 100 squared plus 100 squared. You can almost do that in your head. You end up having need a square root of 2 somewhere. What do you get? Did you calculate it? Yeah. Oh, I thought you had your calculator out. Or maybe it's your phone. Who knows? Or maybe your calculator is your phone. I don't know. Does anybody have a calculation of this? Well, okay. I'll use. Pardon? If you put this in, you get 100 over. That'd be 100 squared plus 100 squared. So that's be a square root of 2 divided by 100. So you basically get, I come up with 212. 212 milliseconds.
Those numbers aren't mine.
They're what?
They're not mine.
That's right, because this is going to be for before the first stimulus, and this is going to be the first stimulus. And then the next diastolic interval is going to go here, and then the next action potential duration is here. So you got to go through somehow. So it really.
So it alternates.
So you're gonna go boom, 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 boom. I suppose you could set it up so you went boom, 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 but it just depends on where you start. Whether you start with the diastolic interval or action potential duration. I want to start with the diastolic interval. Now, how can we see that graphically? Well, what that's saying is if you know that diastolic interval is 100, you just go up 100 up to this point here, and this is 212. Okay? So you know that this is going to be 212. So let's say this is going to be 212, and then it goes back down. And now, what is the next diastolic interval? I erased that equation, but it was a fairly easy one. If you know that this is 212, and we know we're stimulating every 400 milliseconds, so we know that's every 400. How long is that?
188.
188. It's just cycle length minus action potential duration. So 400 minus 212 is 188. Now how can you see that graphically? Well, you could say that if you had the cycle length of, let's see, the easiest way to see this is you really need to have the plot of the other relationship. You have cycle length is equal to APD plus DI for the ith stimulus. And what that really means is that we're going to have a plot here. If I wanted to put it on this graph, I would say that that's a plot of action potential duration equals cycle length minus DI. So if you have a cycle length up here at 400 and you down here at 400, you're really talking about a straight line that goes like this. And if I've drawn it so it's straight, it helps to have a straight edge. You might want to bring a ruler to the exam next time. So if you want to know where this is, you would start here at 212 and you'd basically go over to this line. And that would bring you to, again, if this line is perfect, it would take you down to 188. So you can think of this as a process, graphically, of just going from this point over. So you go from your action potential duration, you go over and you calculate your diastolic interval, and you get 188. You can think of that as just, instead of going back and forth, you're just moving over to this straight line. All right, so now we have the diastolic interval. Now what's the next action potential? So who's got their calculator out? You can put in 188 in for the diastolic interval.
265.
265, that's exactly what I got, or at least within three significant figures. 265, graphically, that's taking 188 and going up, so that's just going up to this curve up here. And then you take 400 minus 265, and you get 135, which is sort of like going back over to this curve. That's equivalent, or in other words, 400 minus 265 is 135. Then you can do it for 135. I won't keep asking you guys to do it. I'll just write some of these. 141, 159, 254, 146, dot, 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 dot. What's happening is you're going around this thing, boom, boom, like this, spiraling in until finally you're going to reach a steady state situation where you're going to have 250, 150. And if you stick 150 in for the diastolic interval, you'll get 250 for the exponential duration. And if you take 400 minus 250, you get back 150. So once it reaches and spirals into this point where these two lines cross, it's just going over and over and over again. So if you looked at this case, you would have, let's see, let's put some of these stimuli down here. You're getting 212, 265, so this one's a little longer, and then a little shorter, and then eventually you're going to reach sort of a steady state situation where it's going to be 250, 150, 250, 150. It's going to go on like that forever. This is a really boring case, but this is a case when you have a really long stimulus, a cycle length. So I wanted to do this case because it's just like all the other cases, except it's kind of the dull one. All you do is stimulate. For every stimulus, you get an exponential, and they end up, except that for a few transients, they end up going, giving you the same thing over and over and over and over. It's an example of nonlinear dynamics where it's, we could call this a one-to-one response. Very simple results. Okay. Questions on how we did that? Again, you're going to do exactly the same thing in the homework. It's just this function has a slightly different form. More or less the same shape, but a different functional form. Well, let's see if we can do something that's actually interesting. So let us start stimulating faster. That's probably the thing that would make this system act a little strange. So we're going to change, and instead of doing 400, we're going to go down to 300 milliseconds. Not horribly fast, but fast. Okay. Now I'm going to have to, I want to leave the axes up here. I want to leave the restitution curve, but I want to get rid of all this stuff. So this gets a little bit messy, but we'll try to do it without starting from scratch. The restitution curve is the same. It doesn't depend on the cycle length. So it stays up there. You got to start somewhere. Let's start at the same place. 100 for the diastolic interval. I might as well erase this part too because this is all changing because we're stimulating faster. So now we're going to be stimulating more like 300. Boom, 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 boom. Okay. Diastolic interval of 100, what is your action potential duration? It's the same as last time because that doesn't depend on cycle length. You get 212. So this is the same. You didn't have to redraw that. But now this diastolic interval is shorter. What's the diastolic interval in this case? 88. 300 minus 212 is 88. So that's the same as going up here. This looks the same as before. But now we want to find 88. What we really have to do is we have to draw a line that goes from 300 to minus 300. This curve has really shifted over by 100 milliseconds. That's what it means to stimulate faster. So we're at 88. So what's the next action potential duration?
198.
198. That's just putting 88 into this function. That's like going over let's see, we went up here, and then we found the 88 was when we went over this curve, and now the 198 is when we went down to this curve. So you might think, oh, it's going to spiral in, but let's see. What's the next cycle length?
102.
102, that's just 300 minus. If you put in the next one, you get 214, and then you get 86, then you get 196. This is spiraling out. Okay, so that's a little interesting, and it keeps spiraling out. And if you do this over and over enough, you'll eventually find, say you do this for about another dozen stimuli. Yes?
Is that supposed to be a comma?
Where? This?
Yeah.
That is a leftover mark from the previous calculation. It's just 86 there, 214 and 86. Okay, eventually this thing's going to spiral out until it finally gets to the point where it's going like this. Boom, 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 boom. And that corresponds to 274, 26, 75, 225, and 225. If I put that into the restitution curve equation, what you get back is 274. So I've left off some of the lines here. It takes a while, but eventually spirals out and gives you this square. And it would look just like a square if I had drawn it carefully. What's that look like here? Well, if you let it go for a while, what you find is long action potential, then a short action potential. 88 milliseconds. Actually, once it reaches this steady state, it would be 274. So let's not look at it initially. Let's look at once it reaches steady state. 274, then 88, then a 274. Not quite that big. Then 88, and so on. Long, short. So what's happening is this one's long, and therefore is a very short diastolic interval. Very short diastolic interval means you get a very short action potential. And that means the next diastolic interval is very long. And that means your next action potential is very long. And that means your next diastolic interval. See, it works going back and forth. This is what is called, in the business, alternans. It means when you're stimulating at a constant rate, like a metronome, but your response is long, short, long, short, long, short, long, short. It's another type of behavior that can come out of just this simple restitution curve. Yes?
So for this one, the total time is 388 instead of 400?
Total time for what?
For the cycle?
This is 300 for the time between stimuli. That's sort of what we set with our knob. We have a knob stimulator with a knob on it. We set that for this problem for 300. Yeah. Where is the? Here, I have. Oh, I see now why it's confusing. I forgot. 88, I didn't want to use 88. I wanted to wait until it got down to 88 was totally bogus. Okay. It's 274.75. This is once it reaches steady state. Sorry about that. 75. I looked over here, and the first thing I saw was the 88. I didn't think about it. Thank you. That's what happens when you don't think. So thank you. Alternans, when they happen in the heart, aren't necessarily a huge problem, but they are a sign that the dynamics is getting a little out of whack. And as we'll see in a few minutes, once it gets really out of whack, you get something that looks like it's turbulence or chaos. So if you see alternads, that's usually a sign that you want to, you want to keep an eye on this, because the dynamics are getting a little bit unstable. But it's kind of like a first-degree heart block. It's not something you have to treat, and it's not an emergency, but it's a sign that you need to keep a watch on the person. All right, so that is another type of behavior that can come out of this. Well, we can see even different types of behavior. So what's the next thing we want to do? If you were doing this experiment, this was in your lab and you were doing this experiment, what's the next thing you'd want to try?
100 millisecond cycle.
Yeah, you'd make it faster. And you wanted to go 100, and we're going to go 100, and we're going to go faster, but I'm going to go a little slower and change it just to 200 milliseconds. So I'm going to turn the knob up of the stimulator from 300, and now I'm going to have it up to 200. So now I got to erase all this stuff again, and we're going to have 200 for the cycle length. Okay. So we're going to start here at 100 as before. We're going to have to erase all of this, but not the restitution curve itself. This gets a little messy, but let me see if I can tidy up. There. Okay, now that's the restitution curve. And what else do I need to do? I need to get rid of these, because now we're going to be stimulating faster. 200. Okay. Initial diastolic interval is 100 milliseconds. So we already know what our action potential duration is. It's the same as before. It's 212. Now here comes something interesting. What is the next cycle length? Well, it's 200 minus 212. It's a negative number. You get minus 12. And what's that mean? Well, what that means is that actually the action potential is still going on when the next stimulus came, which means the tissue is refractory, which means you get no response. So you just got no response to the stimulus. It's essentially the stimulus does nothing, at least in our approximation. It has no effect at all. So it comes back down, ends up to 212. That's 212 now. Ends after 212, and then you get an action potential. Really, the next diastolic interval is going to be what? It's going to be 200, and now you have 12 milliseconds after the previous stimulus, the thing ended. So it's 188. So what way you can write this in our chart is we can say we got nothing for the action potential because it was refractory. But then we just add another 200 beyond this, and we get 188. And now you have a diastolic interval of 188, and you can calculate what the action potential duration is. And if you put that into your calculation, into your calculator, you will get 265. So you get a long action potential. And again, this is 265, but you're stimulating every 200. So your next diastolic interval is going to be negative again. In fact, it's even more negative. It's minus 65. Which just means, again, the tissue is refractory when you stimulate it. But it eventually gets over. And it comes out here for the next stimulus. So what's the next? So you basically got refractory, so you got another dash. And then you add another 100 or 200 to this thing, and you get 135. And then you keep doing this. I would suggest after class you do this for about a dozen. But you're going to do it in your homework, so maybe it's not so important. What eventually happens is you reach a steady state situation where your action potential is 250. You get a minus 50, which gives you a nothing response. Then you get a 150, and 150 will give you another 250. And so on. It just begins to repeat itself over and over. Okay, we need to do two things. We need to see what this looks like on this type of a curve, and we need to see what it looks like up here. This one we've pretty much seen. It's going to keep giving you an exponential a little bit over 200, and you're going to keep getting a refractory, and then you're going to get another one. It looks pretty much like this. And this is called a 2 to 1, so it's no longer alternans. You have a 2 to 1 response. Every second stimulus gives you a response. In the words of cardiac electrophysiology, this is sometimes called a Winkelbach response, after the person who first named it. And what that really means is every other response. Where you can sometimes see this in electrocardiogram is if you have a second-degree heart block where the atrium's firing once every, say, 200 milliseconds, but because the AV node may have a longer refractory period, only every other signal actually propagates through, and so your ventricle is giving a response like this. You're getting P wave, P wave, P wave, P wave, P wave. You're getting QRS, nothing, QRS, nothing, QRS, nothing. That's an example of where you'd see this more specifically. Now this plot's the one that's a little weird. Okay, we started at 100 and we just went up to 212. And then we said, well, we're going to go over to, you get a minus 2. Well, that's because if you plot this curve, it's now over here at 200 milliseconds. And this would come over and hit it negative, minus 12. So what we did is, okay, so we said, well, we're going to add another 200 and go to the next stimulus. That's going over here, 200 milliseconds. That's equivalent to drawing this line back in here from 400 to 400. And that's really the line where you get every other stimulus. So that's just like going over to this line. And then the next one's going up and over and spiraling in again. And you eventually reach a point here, but because you're on this line, you're really in the case where it's responding to every other stimulus. If you were along this line, you'd be responding 1 to 1. This is the 2 to 1 line. So this, generically, it looks like a 2 lines, and you're at the 2 to 1 response. Okay, so if you wanted to use the language of nonlinear dynamics instead of the language of cardiac electrophysiology, what you call this is a period doubling. The period that you apply is 200 milliseconds. But the period that you observe is, well, how often does this repeat? This, basically, once it reaches steady state, this looks the same as this, looks the same as this. It's twice the period, 400 milliseconds. So your period, your response period doubled compared to your applied period. Period doubling is very common in nonlinear dynamics, and in fact, it's one of the routes to go to chaos, is you get period doubling. Sometimes you can get, instead of a 2 to 1 response, you can even get 4 to 1, where you might have long, short, really long, really short, long, short, really long, really short. You can get all kinds of responses like that. All right, so this is fun. What do you want to do now? So Rita, what was your suggestion now?
100.
Let's go to 100. Well, okay, 100's actually, you're going to have to do the 100 on your own. I'm going to turn it down, but I'm only going to go to 150 because that's going to show what I want to show. So we're really driving this hard. Okay, so we're really driving this hard. And now we got to see what happens. Okay, so let's get all this out of here. Get that out of there. Get this. Oh, get these. And 150. And that means you're going to have a line here which goes from 150 to 150. It's going about like that. And you're going to have stimulus after 150. Boom. The first action potential, if we start at 100, the first one is 212. But for reasons that will become clear in a few minutes, I'm going to include a few extra significant figures. Didn't really make much difference before, but it's going to make a difference now. So I'll get this to the nearest hundredth of a millisecond. So what was 212 is now 212.13. It's really just a matter of how many significant figures are keep. So that means 150 minus this, you're going to get a negative number. So we're going to start at 100. We're going to go up to this guy. You're going to get a negative number because you're going to come over here and be looking for this curve. And you actually get minus 62.13, which means you don't get a response, which means you have to wait for the next one, which is 150 later, which takes you 87.87. So that means on this curve, there's a 300-300 curve. Let's see, that's going to just slip underneath where that hit. So what happens next? Well, I'm not going to go through and calculate all these numbers. You can calculate them yourself. But I'm going to, I'll put a few of them down just so you have them on the list here. Actually, it's kind of hard to even write those down. But this one is 98.03 minus 48.03, so you missed one. Then you get 101.97, 214.19, minus 64.19, dash 85.81. So it looks like it's doing its 2-to-1 thing. But you're eventually going to find, it looks like it's doing its 2-to-1 thing, but it's not spiraling in. It's actually spiraling out. This was 212, went down to 98. That went above 212, out to 214. So it's coming in here, but it's spiraling out instead of spiraling in. And eventually you're going to reach the point where it's going to spiral out so far. I don't know if these numbers are exact right. It's going to come over here, and you're going to reach the point where it's going to drop down near this one. You almost have to do the numbers to really see it. And what it's going to do, though, is it's going to come here, but it's not going to spiral into this point. It's going to spiral out. It's going to spiral out until it reaches up and comes up to this one. And then it spirals out again. So what happens is you start getting something that looks very confusing. You start getting some cases where, and it's hard to draw these pictures, but let's see, this is every 150. You'll get short, long, medium, real short. The next one will be real long, and medium, short. You get all kinds of no repetitive response. You get what's called chaos. Chaos is it looks like it's random. It looks like the exponential durations are just random in here, but they aren't random. They're absolutely obeying this rule. But if you just look at the data, it looks like they're all over the place. Deterministic chaos. It's deterministic because it's defined by a rule, but it's chaos is it looks like you got your results from a random number generator. In the heart, this corresponds to you've decayed down into fibrillation. Now remember, this model doesn't have everything. It doesn't actually have waves propagating through the tissue. It's just a point model. So it can't capture everything about chaos, but it does give us sort of this random behavior like you'd expect. So chaos is a generic property of these nonlinear systems that you actually see. So when you're doing your homework problem, you're going to go to faster and faster rates, and you're eventually going to do a rate where I think I asked you to do 20 of these stimuli, so you can really see that the chaos is how it sets up. Make sense? Now, there is something that's interesting about chaos. And I'll show you why. Suppose instead of doing this at 100, I did this at 101.00 instead of 100.00. So just a slight difference in this diastolic interval. So this initial interval is just a little bit longer. Well, initially, you just get a little bit different response. Minus 63.18. You get nothing, and you get a 86.82. But the differences are growing. Until finally, as you get down here a long ways, you get a case where this one comes up, it begins to spiral out, but now when it jumps down to this one is a different time. It jumps down on a different stimulus, and then it begins to spiral out, and before you know it, maybe 20 stimuli later, the results are completely different. There's absolutely no way, no correspondence between the two. They started off 1% different, and in a short time, they are completely different as if they had wildly different random initial conditions. This is called the sensitivity to initial conditions. If it's chaotic, small changes in initial conditions grow into very large changes. Even if you started at 100.001, it might take a little longer, but after enough stimuli, you would be completely different results. One would look like, this is after the transients go away, one would look like this, and one would look like boom, boom, boom. They look like completely different, as if there's completely different responses. So when you're chaotic, it depends very sensitively on the initial conditions. This is known in the business as the butterfly effect, because some of the people who first demonstrated this were studying the weather. So they thought that if you have a system, non-linear system predict the weather, if you input what the temperature and the wind and everything is all over the world, and you have a good model, you ought to be able to predict what the weather's like. But even if your model was perfect, but your initial conditions were wrong because you put in all your wind speeds, but you forgot about that butterfly in Siberia flapping its wings, so you had your wind speed quite slightly wrong. If your results are chaotic, then after a month or two of simulations, the weather's completely different. You have a storm one day, and now the other model, because if you put in the butterfly flapping its wings, you have a beautiful day for your picnic, no storm. So it makes a big difference in systems that are chaotic. So it makes it almost impossible to predict them. Even though you have a completely deterministic model, which may be a correct model, if you're very sensitive to initial conditions, your ability to predict is almost shot. Okay, I wanted to just tell you a little of the history of this. There's a nice book by James Glick called Chaos, Making a New Science. And the fella who first discovered this, his name was Lorenz. And Lorenz was working on a model of the weather. And it was a really simple model of just a convection cell that was going around. He had a temperature and he had a density of the cell and things. And he was working by himself. And what he did, let's see if I can find where I wanted to read. Okay, he had made a computer to do these simulations. He said, with his primitive computer, Lorenz had boiled the weather down to the barest skeleton. So he had a mathematical model. Yet line by line, the winds and temperature and Lorenz's printouts seemed to behave in a recognizably earthly way. So his results looked vaguely right. They matched his chiseled, cherished intuition about the weather, and he sensed it as repeating itself. So, in order to make the patterns plain to see, Lorenz created a primitive kind of graphics where he plotted out these. So it's kind of like this graphics. Now, one day in the winter, in 1961, wanting to examine one sequence at greater length, Lorenz took a shortcut. Instead of starting the whole run over in his computer, he started midway through. To give the machine its initial conditions, he typed the numbers straight from an earlier printout. Then he walked down the hall to get away from the noise and drink a cup of coffee. When he returned an hour later, he saw unexpected something that planted the seed of a new science. So basically, he only did the simulations for say 20 iterations. He decided he wanted to do a total of 40, so he started halfway through and he just input the results from the last one. But the computer was calculating the 6 significant figures, and he only took a shortcut and only input the 3 significant figures. So when he came back, his results were completely different than what they had been before, at least on the parts that overlapped. So he said to himself, what's up? Something seems to be really wrong, but he played around with it and he found out that, well, really his model, although it was a fairly simple model, was really sensitive to initial conditions. This started the whole chaos, science of chaos. So it's 1961. I mean, that's a year after I was born, so it's a fairly recent thing, at least by my standards. You guys may still consider it ancient history. But chaos is a fairly new branch of science. So, are there any questions about chaos in general, or their applications to cardiac tissue, or, in other words, problem 41 of the homework assignment? Okay. Let's look at this a little more and look at what problem 42 says. And problem 42 is just basically looking at these restitution curves a little more carefully. What problem 42 shows is that if you have, here's actual potential duration, and here's diastolic interval. This curve always has a slope of -1. That's just the way it's built. The restitution curve, its slope changes. So it might have a steep slope here. Whereas in another case, in a different part of the actual potential restitution curve, this still has slope -1, but this slope might be less steep. You can just look at general principles. If you start going up on this case, so this is a restitution curve, start going up, over, down, you can just see the thing spiraling out. But here, if you start out going up, down, you can see the thing spiraling in. What happens is, if the restitution curve slope of this curve is greater than 1, it spirals out. And you're going to get chaos, or you're going to get alternads or something. If the slope of the restitution curve is less than 1, it spirals in. So, what this says is, if you want your system to be more stable, what's really important isn't so much the peak of this restitution curve or anything. What's really important is the slope of it. If you can make this restitution curve so its slope never gets above 1, you can suppress all this chaotic dynamics. So the problem asks you to take a new restitution curve, which goes up here, but instead of starting from the origin, it starts up here somewhere. And you can figure out how, exactly under what conditions this slope never gets larger than 1. And so you're suppressing the slope. You're keeping the slope down. If you can keep that slope down enough, you ought to be able to suppress arrhythmias. Yes?
Does the slope of 1 just move in the box? Or does
If it was exactly 1, it would probably just move in that box. It wouldn't grow out. It wouldn't grow in. But that's like trying to take your pencil, and it's unstable. If you had it slightly more than 1, it'll fall over, and slightly less than 1, it won't. So it's sort of an artificial case. So I'll tell you a little story behind this. Is that people originally didn't appreciate this idea of the restitution curve, and they had these drugs that they thought would suppress arrhythmias. And so they decided to do a big clinical study to see how well these drugs worked. So they got a bunch of people, and half of them got the drugs, and half of them didn't. And they went through the clinical study, and they got about halfway through the clinical study, and they decided they had to stop this clinical study. It was ethically impossible to continue, because people getting the drugs were dying at a faster rate than the people who weren't even being treated, their controls. So the drugs were killing people, so they had to stop the study. And these were big, expensive clinical studies. So they said, what happened here? Why do we think we got drugs to suppress cardiac arrhythmias, but they actually are killing people? Well, the answer seems to be that they weren't adjusting the slope of this restitution curve. They were just doing something else to it. And now that they understand it's the slope of the restitution curve, it gives you a whole new way to design your drugs. So people are trying to design drugs that will suppress the slope of the restitution curve, and it's still ongoing. They've done some animal experiments where they have a nice drug that keeps the slope fairly flat. It seems to work great. It doesn't really stop arrhythmias from starting, but it keeps ventricular tachycardia to decaying into fibrillation, which is the chaotic response. Problem is the drugs that they've tested in animals have some real bad side effects, like they block calcium channels so the calcium can't come in so the muscle doesn't contract. So now you have a heart that doesn't go into fibrillation but doesn't beat either. So obviously you gotta fix that. And people are working right now on trying to get new drugs that will suppress these arrhythmias without bad side effects. There's been some progress. There's been no super magic drug that works, but it's a direction that a lot of the pharmaceutical industry is going. And this is somewhat of a simple model. You can add in all kinds of complications, but I wanted you just to see the simple case. So problem 42 is really looking at this question of the interval, strength interval curve and its slope. Okay, what else is there? There's a couple other problems that I wanted to mention. Problem 43 is kind of interesting. It stays on this general theme, but problem 43 shows that in some cases you can have bistable systems, where if you start with the diastolic interval of 100, you get one type of behavior, maybe alternans, but if you have a different diastolic interval of 110, it might go over to a 2-to-1 response. So you can get bistable. Most systems aren't really bistable in that the diastolic interval sort of uniquely determines what it's going to be. It may make the transients a little longer, but it doesn't affect the response. But you can cook up systems that are bistable. Problem 43 looks at that. So that just gives you some more calculations to do. And then problem 40, so we're really talking about these 4 problems. We haven't mentioned problem 40. Problem 40 is kind of cool in that it gives you 2 sets of data and asks you which one is from a chaotic model and which one is from a random number generator. And let me show you the idea is, okay, I'm going to erase all this, but you can make an even simpler model. It's not as relevant to the heart, but it's the simplest, just about the simplest toy model you can come up with. You only have one parameter, x. And x, the j plus 1 response is a times xj 1 minus xj. So the idea is you start with some j, take some first value, select the value of x for the first value, and you plug that value in here, and you calculate the second value. And you take that second value, and you plug it in, and you get the third value, and so on. This model, for certain values of a, will give you chaos. So now you get a bunch of numbers, and you want to figure out whether they're chaos from this model, or whether they're a random number generator. You just look at them, they look both kind of randomish. But what you can do is you can plot xj plus 1 versus xj. That is, you divide all the numbers up into pairs. So you have, say you have a number. Let me see. Let me write down the actual numbers here. The numbers look like something like this: 0.975, 0.0951, 0.3356, 0.8696, and so on. You take the first 2, and you plot this second one is xj plus 1, and the first one is xj, so you plot that. And then you take the next pair, and you treat this as the xj plus 1 at 0.3, and you treat this one as the xj at 0.095, and you get something like this. And you keep plotting those like that. 2 things can happen. They could be from this model. If they're from this model, they'll all fall on this curve. And what's this curve? This is really a parabola. It's an upside down parabola. It looks something like this. So as you go through the data, you'll get point here, point here, point here, point here, point here. But if you do a bunch of them, you'll find that they trace out this curve perfectly. So it looks random, but it's actually got order in it. And then you take the data that's a random number generator, and you just get random numbers. Some might fall in the curve, some might not. Just be all over the place. So if you're looking enough at the data, you can actually distinguish which one has order hidden in it versus which one just doesn't seem to show any order at all. So you just have to take that data and you basically do this plot. It's really often called a phase space plot. And you can tell. And this is the general way, it's a simple example of the general way people analyze data for chaos, is they can analyze it in some weird way that will bring out the order, or if it's random numbers, it won't show any order. So there are ways to distinguish between chaotic systems and random systems. It's just they're not real easy. So those are those 4 problems, and that's what I had to say about chaos. I will give, we have a few minutes left. One last chance. Does anybody have any questions on homework 8 that is due on Friday? Yes.
I am not able to find the VI of X in 8.13.
8.13. Okay. Let me look at the exactly how the problem was worded. 8.13 says the current along the axon is I0. So I'm going to erase this. Completely changed gears now. We're talking about chapter 8. The current along the axon is I0 for 0 less than x1. And 0, it's that, and it's 0 everywhere else. So, here's your axon. This is x. Here is going to be x equals 0, x equals x1. And there's a current flowing. I0. So then it asks you, first of all, what is VI? Okay, did you have any idea how to begin? All right. If there's a current flowing along the axon, then there has to be a voltage gradient along the axon. And in this case, the voltage gradient, remember there's a relationship between electric field and the voltage gradient, there's a minus sign in there. So the voltage gradient would have to be going down. It has to be more positive here and more negative here so that you get this. And that voltage gradient is going to be constant because the current's constant. So what you have is the current, the voltage gradient, the voltage is going to be going down like this. Out here, there's no current flowing. So it's going to have to be a constant potential. Out here, there's no current flowing. It's going to be a constant potential. So qualitatively, VI as a function of x is going to look like this. Then if you want to get it quantitative, you just have to really know what the voltage drop is. And if you know the current is going to be pi a squared, that's the rate, cross-sectional area, times the current density. And the current density is going to be conductivity. There's a minus sign, and that's going to be dVi dx. So, and that's all got to equal I0. And so if you're given I0, you can figure out at least what the gradient, the slope is that way. And then if you just integrate it, and what you take as your 0 point is sort of arbitrary. But you can figure out then what this change in voltage is by taking this and multiplying it by x1. So that's the idea. It's kind of the backwards. We had problems where you were given V as a function of x, and then it became easier to calculate the current. In this case, you have to do the inverse, and rather than actually doing integration, you can just reason it out by that sort of way. So that would be how you get VI. And just so you don't think I did the whole problem for you, that is just the first part. The harder part is finding the magnetic field, which is like what we did in class. Other questions about homework number 8? In that case, I will see you on Friday, and we'll continue talking about nonlinear dynamics related to the heart.